talk is about d-to-1 hardness of coloring three colorable graphs with O1 colors. This is joint work with my advisor Venkat from CMU. We'll first start off by defining graph coloring. Graph G is said to be k colorable if there is an assignment of k colors to the vertices, such that for every edge, the endpoints get different colors. And we'll mostly focus on three coloring in this talk. So three coloring is a very standard NP-hard problem. That is like given a graph G, finding out whether it's three colorable or not is very hard. And so we are interested in approximation algorithms for this problem. And what do I mean by approximation algorithms? By that I mean given a graph G and that is promised to be three colorable. The goal is to color with some C greater than three colors, but in polynomial time. Like for example, can we like color it with 4 colors or 10 or log in or even like n-1? And so one of the earliest results in this approach is due to Venkatesan from 1983. He gave a very nice combinatorial argument to show that you can always color it with square root n colors in polynomial time. And there's been quite a bit of work on this front. And the best result currently gives something slightly better than n to the 0.2 colors. And the tools used for this direction are typically combinatorial approaches combined with semi-definite programming. And now we'll take a look at what's going on in the hardness front. And on the hardness front, things are much more dire. And we'll first look at the decision version, which is easier to think when we are dealing with hardness. And in the decision version, it's the same as before, but you just need to distinguish between two cases, given a graph G. And the first scenario is when G can be colored with three colors, or G cannot even be colored with C colors, if C is like greater than. If C equal to 3, that's the standard three coloring NP-hard problem, which is like distinguishing whether graph is three colorable or not. And now this problem, it's C equal to 4. There's been it's known for quite some time, and C equal to 5 is actually proved very recently by Boolean Krokenau Opperschall using quite a bit of technical algebraic machinery, and it's open even for C equal to 6. So there's like a huge gap between algorithmic front and hardness front. On the algorithmic front, we can only color with something polynomial in colors, but hardness we can even show like for 6 colors. So to get around this issue, people have worked on conditional results. That is, you assume some other problem is hard, and in that case, can you prove that three coloring is also hard? One natural problem for proving this conditional results is the unique games conjecture. But the problem with unique games conjecture is that it requires perfect completeness. And so by itself, it cannot give hardness of three color. And so Diener, Mossel, and Rajev have worked around this by assuming certain Fish-shaped variant of unique games conjecture. They also proved that 2-to-1 conjecture, which is also a different variant of unique game conjecture. Under assuming that conjecture, we can prove that 4 versus C coloring is NP-hard for every C. Not that this is a harder problem and so easier to prove hardness. So all these conjectures, unique game conjecture, 2-to-1, or even the Fish-shaped variant, all these are different forms of label cover problem. So we'll first start off by defining what label cover problem is. Label cover is arity to constraint satisfaction problem. That is like you have an underlying set of variables and there's a label set and there are constraints between pairs of them. And even more structured, we can think of there's a bipartite graph with partitions being L and R. There's an alphabet sigma, a finite alphabet. And for every edge in the bipartite graph, there is a constraint pi e. And the important point is that this constraint is a projection constraint, or more informal, it's a function. That is, for every assignment to the left variable, there is only one assignment on the right variable that satisfies it. And in the unique games conjecture, this pi is actually a bijection. So like for every assignment on the left, there's unique assignment on the right that satisfies this condition, and the same holds for the other direction as well. But in general, it's only one direction. Like for every assignment, there's one assignment on the right that satisfies it, but there could be multiple assignments on the left that satisfy a condition for like a single assignment on the right. And this problem label cover is known to be very hard to approximate. Like it's NP hard to distinguish between the cases that all the conditions can be satisfied versus only an epsilon fraction of the conditions can be satisfied for any epsilon arbitrarily small. And this the case when all the conditions are satisfied is usually referred as the completeness case, and the other case is called soundness. And as I mentioned earlier, we need perfect completeness for the three coloring. And what do I mean by perfect completeness is that in the completeness case, all the conditions are satisfied, as opposed to 1 minus epsilon fraction of the conditions being satisfied, which is the case for unique games conjecture. Now we look at d-to-1 conjecture. So as mentioned earlier, these conjectures are all a variant of the label cover problem hardness. So we have already defined the label cover problem, and so in the d-to-1 conjecture, it's a special case of the label cover problem when the constraints are even more structured than before. So previously I mentioned that the constraints are of this projection form, but in the d-to-1 instances of the label cover, the constraints have very structured form of projections. So for every element on the right, there are exactly d elements on the left that can satisfy that particular constraint. So here, like it's you can think that for vertices on the left, the alphabet is dl, and on the right, it's 1 to l. And for everything in the uh, right side label set, there are exactly d of them that satisfy the any constraint. Like this pi is one of the constraints in the ring. And if one-to-one conjecture is basically the unique games conjecture, and unique games conjecture you cannot assume perfect completeness, but for d-to-1 you can. And Diner, Marcel, Raja have proved that 2-to-1 conjecture suffices to prove for a C problem. And our main result is that any uh, d-to-1 conjecture is sufficient to prove hardness of 3 versus C coloring. I have to tell that this d-to-1 conjecture with imperfect completeness, or even the 2-to-1 conjecture, was proved recently in a long line of works. And one might hope that d-to-1 conjecture with perfect completeness might be easier to prove rather than just 2-to-1 conjecture. So our result shows that even if one proves that, it suffices to prove hardness of 3 coloring. First, prove that d-to-1 conjecture implies that 2D versus C coloring is NP-hard for all C. And now it turns out that this is sufficient to prove hardness of 3 versus C as well, due to an amplification result by Krokin, Opreshal, Rosna, and Zivny. They argue using the properties of chromatic number of arc graph. Arc graph is line graph. That if you want to prove that T versus C is NP-hard, it's sufficient to prove that some B, there's a function B which is like 2 to the n over square 10 roughly, and if it suffices to prove that BT versus B of C is NP-hard. So if you want to prove, for small t, it's sufficient if you have like a large enough BT where like if you prove that 2D versus C is NP-hard for all C, it suffices to prove 4 versus C as well, for like if you prove it for any D. And they also get 3 versus C by like a slight modification of this argument. And so our updated goal is to show that d-to-1 conjecture implies that 2D versus C coloring is NP-hard for every C, and D could be any arbitrary constant. And in particular, if D equal to 2, this is precisely what Merzel, and Regev proved. And their approach is to use label cover long code based deduction, and they combine this with invariance principle based approach. And we also mimic their approach, and there's a key part where we differ from them. So, and that key step is the existence of a symmetric Markov chain. And for their deduction to work, they needed to show an existence of a symmetric Markov chain with certain properties, and we will also do the same, but we will do for a general D rather than just for D equal to 2, and then we'll be done. And we'll start off by giving a representation of a symmetric Markov chain. Symmetric Markov chain just is a Markov chain, but the transition probabilities are symmetric. And if you don't know what symmetric Markov chain is, it's you can think of it like a doubly stochastic matrix, and that is symmetric. And what kind of symmetric Markov chain do we need? Our state set is 2D to the D, vectors of D dimension, and the elements of the vector come from 1 to 2D. And we need two properties of this symmetric Markov chain. First, we need that the transition probabilities are non-zero between two vectors u1 to ud and v1 to vd, only if their support is disjoint. That is like there's no element that is present in both u1 to ed and v1 to vd. And second condition is that the spectral radius of this symmetric Markov chain is not equal to 1. Okay, and how do we show existence of such a symmetric Markov chain? And for d equal to 2, Merzel and Regev, they constructed such a symmetric Markov chain manually, and we need to construct that for any general d. And how do we do this? So the idea that we use is matrix scaling. What is matrix scaling? So matrix scaling is a very generic approach to to construct a double stochastic matrix. There are a lot of other applications, but for us, we'll think of it as a procedure to convert a general, an arbitrary symmetric matrix that is non-negative to a double stochastic symmetric matrix. So in particular, we'll start with the adjacency matrix of an undirected graph. Okay, and as long as there is a row or column that whose sum is not equal to 1, I mean, if you start with an arbitrary graph whose degree is not equal to 1, this will be the case. Just divide that particular, all the elements of that row or column by S. And you can keep doing this procedure till whenever there is a row or column whose sum is not equal. The main question then is, when will this procedure terminate? Turns out that under some special conditions, this procedure actually terminates, and we'll discuss which conditions they are. So the conditions, you can think of the conditions as requirements of the graph that you start with. So essentially, like if your graph satisfies certain property, there is a way to do this iterative procedure to end up with a double stochastic matrix. And the Singhorn and Knopp in 1967 proved that if that underlying graph has something called total support, then it's sufficient to prove that there's this iterative procedure outputs a double stochastic matrix. And what is total support in this context? So they mean that every edge of the graph is part of a cycle cover. Cycle cover is a union of vertex disjoint cycles, and that cover all of the vertices in the graph. And so this total support requirement on the graph is needed to construct that double stochastic matrix, which is the symmetric Markov chain. So overall, we can translate everything all the conditions that we need so far into this required graph on 2D to the D. First of all, we need to show that the symmetric Markov chain exists and that particular procedure outputs it. And for that, we need to have the property that every edge is part of a cycle cover. That is just to show that M exists. And next, we need that M has this disjointness property, where like if there is a transition probability non-zero between U1 to UD and V1 to VD, then the set set of U1 to UD and V1 to VD are disjoint. So this essentially means that if there is an edge between U1 to UD and V1 to VD, then these two sets are disjoint. And the final condition is that we need that spectral radius of the Markov chain is less than 1, which is equivalent to saying that this graph is connected and is also not bipartite. So how do you construct a graph satisfying all these properties? We do it by just starting off with the empty graph on this vertex set. Here Q equal to 2D and adding edges in two phases. So in first phase, we just add edges between all U and V such that their support is disjoint, U1 to UD and V1 to VD into 65. And U and V are of the same ordering, as in for every ij, either ui equal to uj, if and only if vi equal to vj, and ui greater than equal to greater than uj if and only if vi greater than vj, and the other thing is true as well, just from these two. If ui less than uj, then vi also less than vj, if and only if. So why did we do this? So we could add all the edges between U1 to ED and V1 to VD, U and V if their support is disjoint. But then the issue is you can no longer prove the uh, cycle cover property, that every edge in this graph is contained in a cycle cover. By adding edges in this way, we have added edges so that these, for every ordering, these edges that we are adding, they form a condenser graph, and condenser graphs are regular, and so once the graphs are regular, every edge is part of a cycle cover. And so this just the way we add edges ensures that every edge is part of a cycle cover. And next, we still haven't proved that the graph is connected and is also not bipartite. And in order to do that, we add edges between all U and V, where at least one of them is like, type all equal ordering, like all U1 equal to UD. So these edges ensure that the graph is connected and is also not bipartite. Of course, there's other aspect to this. Once you have added these edges, you still need to prove that even these edges are part of a cycle cover. And this step is not really hard. You could just modify the other cycle covers to show that even these edges will be part of a cycle cover. So just by adding edges in this manner ensures that your graph has all the three properties. First, you note all the edges that you're adding between vectors whose support is disjoint. So the disjoint support, which is condition 2, is always satisfied. And since we are adding the second phase edges, the graph becomes connected and not bipartite as well. And the first property is true because that this is a union of condenser graphs, and also after adding even the type 2 edges, the property is still maintained. So since all these three properties are true, then once you run the iterative algorithm, you end up with a symmetric Markov chain, which has all the, both the properties that we have mentioned before. So the idea is simple. Now we substitute this Markov chain in the Mossel radius approach, and then we prove that 2D versus C is hard as well, assuming d-to-1 conjecture. Focus on the reduction from d-to-1 conjecture to the coloring problem using the symmetric Markov chain that we constructed so far. First, the reduction is actually done from D to D conjecture instead of D to 1. And it turns out that D to 1 conjecture implies D to 2 conjecture And d-to-2 conjecture is a variant of d-to-1 conjecture that it's almost as what you can see here in the figure. So in d-to-1 conjecture, for every constraint, we have d things on the left and one assignment on the right that satisfies it. Here instead, you have d2. It's like for every assignment on the left, there exactly d on the right, and the same holds, and they are structured in this manner. One important point to note is that these constraints are no longer projections. These are arbitrary relations because every assignment on the left doesn't quite imply any fixed assignment on that. And furthermore, there's no bipartiteness here since all the label sets are the same size. It's on a general graph. And the conjecture is the same. In the completeness case, you have all the assignments are satisfied, and in the soundness case, you have only epsilon fraction of the constraints. There's a slight difference in the actual conjecture says that you actually have epsilon size fraction size subset whose all constraints are satisfied. No epsilon size subset satisfies the property, but we won't go into the details. So the reduction is the standard label cover long code type reduction where we replace each node of the label cover instance with a bunch of nodes of the graph. And the goal of the reduction is to output a graph so that if the label cover is satisfiable, the graph can be colored with 2D colors, and if the label cover is not satisfiable or far from satisfiable, and this graph, in that case, this graph doesn't have a large independence. The way we achieve is this by replacing each vertex of the label cover with a set of nodes. And you can think of the assignment of coloring of these nodes as some function from 2D to the DL to 2D. And which edges do we add? The main motivation when we are adding edges is to make sure that dictator functions satisfy the all the constraints. As in, like if you set each fv to be a dictator on ith coordinate, fu on if u is an edge in the label cover, uh, if you set u to some assignment I and v to j that satisfies the label cover constraint, we want to ensure that there are dictator functions that satisfy that are a valid coloring of the graph that is resulting from this reduction. And we use that symmetric Markov chain to do so. The key property is that the symmetric Markov chain has this disjoint support property, which ensures that the dictators will satisfy. And the pi 1 and pi 2 are just a representation of the constraint pi e. So essentially what we have done is converted this pi e into this graph. And as I mentioned before, the completeness case follows from just the disjoint support property of the symmetric Markov chain. And for the soundness, we need to prove that if there's a large independent set in the graph that we constructed, there's an assignment satisfying large fraction of constraints in the label cover itself. And we do this by using a invariance principle based approach to find a small set of labels to each vertex that satisfy these constraints. And this is where we need the spectral radius of the Markov chain. And this is also where heavy machinery of invariant principle based techniques are used. But most of them are black box type things, so we don't really go into these details even in the paper. And so this whole thing is actually it's present in dinner muscle regular paper as well, but I just gave an overview here. And to conclude, we in this work we proved that d-to-1 conjecture for any fixed d implies that 3 versus c coloring problem is NP-hard. And we did so by constructing a symmetric Markov chain and plugged it in the dinner muscle regular paper. And finally, one intriguing question is that what is the exact boundary, or like what exact property of the d-to-1 conjecture do we need? We need that the conjecture itself says that soundness to be arbitrarily small for a fixed d. But does it, like, can we make a weaker d-to-1 conjecture where the soundness is something like 1 over d squared? Then is that d-to-1 type conjecture, sufficient to prove our result? Or or do we need what exact functionality do we need? Thanks.